Hello everyone. In the last video, we saw how Boole and Shannon laid the foundation of the digital design systems using two states, 0 and 1, or true and false. In today's video, we're going to understand the difference between analog and digital signals. Let's start with the first one, the analog signal. The analog signal is a continuous representation of the physical quantity. To understand the meaning of the physical quantity, let's take some examples. A physical quantity can be something like pressure, speed, temperature, light intensity, or even the joystick. So in our real world, we have many other examples for the analog signals. But for the purpose of today's video, I think 5 examples are enough. Anyway, before discussing the differences between analog and digital, I think we have a problem here. So we know that digital systems deal only with 1 or 0. And in real hardware, we know that 1 refers to 5 volts or a range around 5 volts. And 0 refers to a range around 0 volts. That means that digital systems deal only with electrical signals. And an electrical signal can be voltage or current. On the other side, we have physical quantities like the pressure, the speed, light intensity, and so on. But those physical quantities are not electrical signals. That means that the digital systems cannot directly deal with the physical quantities. And we need something in between that translates or converts the physical quantity into an electrical signal. And after that, we can take the electrical signal as input to the digital systems. The unit in between these two sides is called sensor. So we use sensors to convert the physical quantities into electrical signals. To understand this more, let's take a real example. The LM35 sensor. This sensor is a temperature sensor. It reads the room temperature and converts it into an electrical signal, into voltage. And as you see, it has 3 pins, 2 of them for powering the IC, for powering the sensor, because we know that any integrated circuit or any IC or any sensor needs a power to work, a power source to work. So we connect the power source to these 2 pins, and this pin is the output. And as you see, it is called V out, which refers to the output voltage. That means it reads the temperature and it converts the temperature into voltage or to voltage. But here we have to have a relationship between the temperature and the voltage, because at the end we read only the voltage by our digital system, by our computer, for example. And then we need to display the temperature at the end. We don't just need to display the voltage. When we are building an application to any company or a farm or something, they don't want to look at a volt. They want to look at a temperature. So the sensor reads the room temperature, converts it into voltage, and in our computer, we convert the voltage back to a temperature value. And to do so, we need to know the relationship between the temperature and the output voltage. And this is our relationship. The equation says the output voltage in millivolts is equal to 10 multiplied by the temperature in degrees Celsius. That means if we have a temperature equal to, so if temperature is equal to 50 degrees Celsius, then the output voltage is equal to 10 multiplied by 50, which is equal to 500 millivolts, or this value is equal to 0.5 volts. Okay, this is how the sensor or the LM35 sensor works. But to understand this more, let's look at this graph. This graph represents the output voltage from the sensor. We have here the output voltage and we have here the temperature values. But the temperature values are not aligned with the voltage, because if you look at the maximum value here, 0.4, you will find that it is aligned with a value in between 20 and 30. Instead, it should be aligned, it must be aligned with the 40 degrees Celsius according to this relationship. But anyway, I should have adjusted this, but I forget. So this is the analog signal, and we say that it is an analog signal because it has continuous values at each moment, at each instant. So it is not something like this, like digital signal. It is a continuous because it has values at every moment. As you see, this is time, and this is the output voltage, and this is the first example for the analog signal. Let's take another example. The joystick. This is how the joystick looks like, but this is how the internal architecture of the joystick looks like. It has a potentiometer or a variable resistor, and we have here a mechanical part that moves around the potentiometer when we play with the joystick. And this is how the circuit looks like. We have a potentiometer. The potentiometer usually has 3 pins. One should be connected to the VCC, one to the ground, and one represents the value of the resistor that we change according to the joystick position. We measure the output voltage from here, which means that the position is converted finally into an output voltage. So the position which we can consider it as a physical quantity will be converted into voltage, which is an electrical signal. So this is another example, and as you see, this is how the output signal will look like according to the positions that we use during our game. A third example, the sound. When we talk or when we have any sound source, this sound source makes variations in the air pressure. As you see, we have variations in the air pressure. We use the microphone to convert the air pressure variations into an electrical signal. It has an internal mechanism that consists of many parts like the diaphragm, the voice coil, the magnet, and so on, to finally take the air variations and convert that into electrical signal. That is how it works, and that is how the signal, the final output, will look like. So this is the third example. I think that is enough for the analog signals. But we have disadvantages of the analog signals. The first one is noisy. It can be affected easily with noise, and it has infinite values. Let's take the first one. As you see, we have a gray line here. This gray line is the main analog signal itself, the ideal analog signal. And we have a noise here. One example of the noise might be the background sounds when you are talking on a microphone. This is considered a noise, and you have to use some programs like Audacity or any other program to remove the noise from the background, and that is how they process the noise and the ideal signal. But I am not going into the details of this because we need to focus on the digital systems. So the ideal signal can have some noises. So what is the problem with the noise? The problem is at this value we have another value, not the ideal one, not the ideal value. So instead of having, let's say, 3.1, we will have 3.3. That means that the signal changed, right? But for digital, I told you that 1 refers to a range of volts. But here I am drawing the logic, not the real hardware values. So even if you put some noises here, if you have noise here, this is not going to affect the 1 value because it is still 1. And the same applies for the 0. So this is a disadvantage for the analog signal, and this is an advantage for the digital signal because it is not easy for the digital signal to be affected with the noise. Then we have this word. The analog signal is infinite. Why it is infinite? Because even if you take a small area here and you try to read the values in between, you will find that these values are infinite values. What do we mean? Let's say that this value is 3. What is the next value? The next value is 3.1. And the next is 3.001, 3.0001. So we have infinite values. So what is the problem with that? The problem is, can we store infinite number of values in a limited memory, in infinite memory or not? The answer to this question is no, we cannot do this. That means that we cannot store the analog signals in our computer or in our digital systems. But we can do this for the digital signals. So that's why we need to convert from the analog to digital. And that is the main purpose of today's video. So we have two conversions here. We have a conversion from the physical quantity into an analog signal, and then we convert the analog signal to a digital one. By the way, there are many sensors that convert the physical quantities into digital values, but this is out of our scope today also. So the analog to digital converter consists of these 3 stages. The analog to digital conversion consists of these 3 steps. We need a sensor, so the sensor takes a physical quantity and converts it to electrical signals. And we need ADC or analog to digital converter to take the analog signal and convert it into digital, and then we take the digital values and store them in the memory. These are the steps, and this is how it looks like. We have an analog input here. This can be represented by a sine wave, as you see, or any other analog signal, like the examples that we mentioned in the previous slides. And this is called the VN. And this is the ADC, and this is how it looks like. And these are the steps to convert analog to digital. These are the steps that explain how the ADC works. The first step is to do something called sampling, and then quantization, and then encoding. And this is how the output of the ADC looks like. As you see, I want to explain this example. We have here 8 bits. That means that we take any value like this value and convert it into 8 digital bits. So it might be something like this. So if we have here, let's say, if we have here this value is equal to 3.1, we can take and read this value and store it as 3, not 3.1, because here we have integer values only. The output of the ADC is integer. So we can represent this by 3, and I'm going to explain why. So the value here will be 3. So the 3 value here will be 1, 1, 0, 0, and then we have 4 zeros. And we also will understand in this course how to convert 3 into 1, 1, 0, 0, and 4 zeros. So this is how it looks like. But we need to look at a simulator that we have, that I built on Gemini, to understand this operation more. If we have a 4-bit here instead of 8 bits, we will have limited outputs, which means if we have 8 bits, then we can represent any value here by 2 to the power of 8. And this value is equal to, I think, 256. So we can represent any value here by any value from 0 to 255. This equation also will be explained during this course. There is a question here, how can we represent the negative values, but this is out of the scope, because, by the way, the ADC should be explained in the electronics course, not in the digital design course, but I'm just trying to simplify things here. If you convert 3.1 to 3 here on this side, you have to, in your software like MATLAB or LabVIEW, you have to convert this value again to the temperature or the physical quantity.